Hi, and welcome to this video. I'm Kristen Kinsevich. I'm a doctoral student at Regent University, and this example will be going through Chapter 9 regarding discriminant analysis. This is using the Tabachnick and Fidell textbook using multivariate statistics. I have the 5th edition, so if I refer to page numbers or sections, it will correspond with the 5th edition. Much of this chapter has to be adapted because I am using SPSS, and the example that they provide in the chapter when they go through the complete example, which is section 9.7 or section 7, they use SAS for their examples, so the syntax and outputs will not be correct, although the results should be approximately the same. Some of the calculations are different, and so there is some slight discrepancy, but it shouldn't impact the interpretation of the analysis or the results. So we start with obtaining the right data set, which right here is discrim.sav. So that's the discriminant analysis data set that they are using in this chapter. And so you can download that if you don't already have it. And I am going to go ahead and open it up. And here we have a total of 465 cases. If we scroll down all the way to the bottom, we can see the total number of cases right now is 465. That's what we're starting with. But we're going to begin with assumptions testing. And the first thing we have to do is clean up our data set and assess the group sizes and look for any missing data. So I'm going to be following along table 9.15, which is on page 425 in the 5th edition. In the 6th edition, it might just be called table 15, and that's just the checklist for a direct discriminant analysis. So all of the assumptions testing that we're going to go through, or the issues, we're going to go through in that order. And we're going to talk about the major analysis, looking at the specific discriminant functions, the plots, and the structure matrix. That's also called the loading matrix. We're going to look at effect size and confidence limits. And we're going to look at variables separating each group with the effect sizes and confidence intervals. And then for an additional analysis, they have a variety of choices. I am only picking one of those, so I looked at the group means and standard deviations for the high loading variables. And high loading just means the ones on the structure matrix that were significant. So that's what I'm going to be doing. The book does describe the pooled within group correlations, and they do a jackknifed classification and cross-validation. I am not going to cover that in this video, so if you're interested in that, you'll have to dig through that part yourself or find another video. Dr. Todd Grande is a great resource on YouTube, and he has a lot of statistics videos, and he certainly understands all of this a lot more than I do. So I'm just going to go through what I did on each step, and you can follow along. Before I get into that, I just want to go over kind of the point of discriminant analysis. So the point of it is to understand the association between a set of groups and a set of predictors. Now the groups are all on one variable. In this data set, it's called work stat, and that's right here. If we go to the variable view, we can see that the work status values is a 1 for working women. So this was a comparison of women who were working or not working. If they were not working, they were called housewives. So this is a data set from the 1970s. So pardon the language a little bit on some of this, but they looked at working women, housewives that were satisfied with their role. So that's group number 2. They called it Hap House, I guess, for being happy. And then group 3 was unhoused, so unhappy or role dissatisfied housewives. So those are our 3 groups. And our predictors are going to be a set of scales. And actually, while you are looking at this section, just go ahead and change locus of control from ordinal to scale. It's been a scale in all the other examples in this same exact data set. And I don't know if that distinction matters in our analysis, but it's more accurate to say that we have 4 predictors that are on a continuous, are continuous variables. So we are not going to be looking at this socioeconomic level. That's another scale. So if that's in your way, because it's kind of smushed in between the variables we care about, you could delete it. For the purpose of this exercise, we won't need it. Obviously, in a real data set, you would not want to do that. We're going to be looking at locus of control, attitudes towards current marital status, attitudes towards the role of women, and attitudes towards housework. So those are our 4 predictor variables. And so our research question is, can the combination of scores on the scales for locus of control, satisfaction with marital status, attitude towards women's role, and attitude towards housework predict membership in the following 3 groups: role dissatisfied housewives, role satisfied housewives, and working women? Now, you could word that a variety of different ways, just depending on how you want to kind of phrase it and use your own language. But ultimately, you're focusing on the combination of these attitudinal scales and how that combination can predict which group each case would fall into. So that's really what we're looking at in discriminant analysis. Now, it's similar, in particular, this example is similar to an ANCOVA, which is assessing variance between groups and within groups. So it's kind of taking 2 measurements of variance between groups and within groups and adding those together. And in this case, we have some covariates because we've got 4 predictor variables. So that's where it's kind of similar to that. It's actually really also, if you think about it, kind of the opposite of a MANOVA, because a MANOVA would be looking at multiple dependent variables. I don't have this right in front of me, and I don't want to say it wrong. But in MANOVA, we would have kind of multiple, independent variables, really. And then, I'm thinking about this, and I don't want to say it wrong. It's so easy to confuse these dependent and independent variables because they keep switching back and forth with each of the tests. So let me just look back here because I had it written down for the last video. So I should go back and watch my last video, or you could, and you will see more. But let me see. So the MANOVA, has 1 independent variable and multiple dependent variables. And then the MANCOVA obviously controls for the covariates. So the reason it's reversed is because in the discriminant analysis, the categorical variable is the independent, essentially, and the predictors are the ones that are the dependent, and it would be the opposite way in MANOVA. It's also similar to regression because ultimately these functions are equations. So that's when you see function 1, function 2. It's really equation 1, equation 2. And so it's basically looking at the variance between groups and within groups, and then using that information to try to guess which group a particular case would be in. And so your function 1 is kind of the equation using the coefficients that they came up with after analyzing the variance. They came up with coefficients that, similar to in a regression equation, you put that kind of, it weights certain predictor variables. So you would end up being able to calculate a score for any given case using the coefficients that you get in the discriminant analysis. So you would kind of multiply the z-score for each predictor variable by its coefficient, and then that would give you a total score for each case. And so we'll talk about that again when we go through and actually do the analysis. And when you look at the plots, you'll kind of see how that works. Okay, I think that is all of the introductory information. So we will go ahead and now look for missing data. So if we go back to the data view, before we split the file to look at the different groups, we're going to get some frequencies just to have the histograms for each of the predictor variables on the whole data set. So go to Analyze, Descriptive Statistics, and Frequencies. And we just want those 4 predictors. So it's locus of control, attitudes towards current marital status, attitudes towards the role of women, skip that socioeconomic one, and then attitudes towards housework. So you should have those 4 variables. Let's click on Statistics. And it would help us to get the mean and all of these things. I'm trying to think, actually, should we do that when we split the file? Yeah, you know what? Well, let's wait on that because we don't need that. We'll put the mean on there and actually the skewness and kurtosis, because we are going to want to look at, yeah, trying to think if we want the standard error of the mean too. Let's put that on there. We're going to run this again after we split the file, so that's why we don't need all of it right away. I'm thinking about what we actually want. And what we want is to be able to look at the normality on the predictor variables. So in this test, yeah, we're looking for missing data, but we're kind of skipping that and doing something else first, just because once we split the file, then I don't want to go back and forth. So I'm a little bit skipping ahead to the second thing in the list, which is normality of sampling distributions. So we're actually going to get that first. Let's click continue, and charts, we're going to want our histograms with the normal curve. Okay, so let's run that. Sorry to do this a little out of order. It's just a little bit more efficient. So it actually shows us our missing data right here. And we could use this anyway instead of splitting the file, or we'll have to split the file to look at some things. But yeah, we could just go ahead and find our missing data right now. I guess part of the problem is right now, if we were to just delete this missing data, like, okay, we got 5 missing on attitude towards current marital status. If we just deleted that without looking into it further with the file split, we wouldn't know if all of those women were in the same group. And if they are all in the same group, it might make a difference. Right now, we actually don't know how many women are in each of the 3 groups. So let's say there's only 15 in the dissatisfied housewives group. And of the missing data, let's say 5 of those are all in that same tiny little group. Well, now that's important because that probably means something about your data. So don't delete anything yet. We're going to split the file and see where exactly that missing data is. And if it's kind of scattered throughout the groups, these here where there's just 1, that'd be fine. But this 5 on the same variable is kind of concerning. What we really care about for this particular first output is really just the histograms. And so as you're looking at normality of sampling distribution, again, this looks at specifically normal distribution of the scale scores. So that's not 100% telling you whether the sampling distribution is normal. You can't really test for that, but you can kind of look for clues. And so that's what we're doing here. So if all the variables are normally distributed and the group sizes are about the same, or at least big enough that we can run our tests, then we will assume normality of sampling distribution. So looks good for locus of control and attitudes towards current marital status with a bit of skewness, but not so much. It still follows the curve pretty well. That's a beautiful chart right there on attitudes towards the role of women. And then attitudes towards housework. Looks good, but let's pay attention to this little guy over here. That's going to tell us that we have at least one univariate outlier. And so let's just notice and keep in our head for the time being that the scores here are really, there's mostly like above 10, but there's at least one, or maybe it looks like even a couple, depending on how many are stacked up right here. But if this is like 1, 1, 1, this might be 2 cases where there's this low score for some reason. So that's gonna this histogram is gonna be evidence that there's at least a couple univariate outliers. So you're gonna want to put that in that section as well. Okay, go ahead and save your output because that's always a good idea. Discriminant output 1. In case sometimes I have more than one output, depending on how cumbersome it's getting to scroll between tests. Okay, so now we've got that data for the whole file, and we want to now split the file so that we can look at the groups separately and figure out where the missing data is and if it's kind of spread out. We also want to be able to do assess for linearity, and we can do that through a matrix scatter plot. So basically, let us just assess the missing data first. We're going to go down to data and split file. And we are going to organize our output by groups, and it's going to be those work status groups right there. Now, technically, work status is a nominal variable, and so we should really change that too, just to be accurate, but it's not going to matter right now. So let's split the file and then go do that. So we'll click OK, minimize the output. Now, before we forget, let's go over to variable view and change work stat right here to nominal. Okay, save your data set every time you make some changes. All right, so going back to data view here, now we want to analyze those frequencies again. We want these same variables. Now remember, it's already going to categorize them for us by the work status groups. So the statistics we want this time, we want the mean, and also we want all of these things because we want to kind of compare the groups. And the charts, you could run again. We're going to assess multivariate normality through a regression later, so we really don't need the histograms. Maybe they would tell us where those 2 univariate outliers are, but we're going to also be able to find that in the frequency tables, so there's no reason to have 12 histograms taking up space. So we'll just display the frequency tables with all of that info in it and go ahead and click OK. So now you're going to scroll up to the start of this one. all the way up. Here we go, frequencies. Okay, so here's the working group frequencies. Let's see how many cases are in this group, first of all. Looks like 246 so far. Obviously, with the missing data, there's fewer cases, but still, that's a pretty large group. So the fact that 4 out of, there was originally 5 missing on this variable, that's a pretty large group to take away 4 from. We're not worried about the 1, that's pretty small. Let's find out where our other missing data point is. So scroll down through these frequency charts, and okay, it's not on the satisfied housewives there. There's no missing there, but there is a missing for locus of control in this one. And then let's see, then it must be the dissatisfied. Yeah, so essentially the missing data is kind of spread out. There's one here, there was one on the locus of control in the previous group, and then a few. And here we can see, okay, there's 81 or 82, 81 once we delete the missing data in that group. And in the second group, it's 136. So clearly the working women group is the largest. And we're actually going to account for that when we do our discriminant analysis, because 246 compared to the smallest group of 81 is a pretty big difference. And so we want to kind of account for that and weight that group a little more heavily in our calculations. So go ahead and click Save again, just so we save our output. So essentially now that we have identified where the missing data is, then we can go ahead and say, yes, it's across all these different groups, and now we just need to find it. Now, a quick and easy way to do that is to sort each variable by ascending. That way you can just find where the zeros are and delete them. Because we already know which groups they're in, we don't have to kind of visually look at that through comparing that with the work status. So we're going to click on Control, right-click, and you should be able to sort ascending, which is going to start with the lowest number and go up. And so here is that missing case that we had. And so we're going to just click on that row and click Delete. Now we're going to do the same thing for the attitudes towards marriage, sort ascending. Okay, now remember we had 5 cases, 1, 2, 3, 4, 5 zeros here. So you can click on 1 through 5, hold down Shift, I think, yep, and then delete that. Now let's sort by the attitudes of roles. Oops. Well, maybe was there no missing data on that one? Yeah, that's probably no missing data because there was 1, 5, and then 1 over here. Yep, so there was none missing on attitude role. So now let's do the same thing for the attitude of the housework. Okay, now this is a tricky one. It took me a while to figure out. There's no zeros in here, so it seems like there's no missing data. However, the 1 is outside of the possible range of the scale, and so that is why it is the missing data. So it is a value of 1, and we're going to delete it. Now, while we're here, we have already determined that the attitude house variable, remember from our histogram, the first one we did, we noticed that there were a couple outliers, univariate outliers. Here they are right here. There's 2 values of 2, and if you look at the case sequence number, it's 346 and 407. The book mentions these, and as we're going to see in a moment, these are also going to be multivariate outliers. But for now, we just only have tested to know that they are univariate outliers. So we've deleted the 7 cases of missing data, and that gives us 458 cases now that we're working with as we assess the outliers. So we still don't know where our final numbers are going to land in terms of group sizes, but so far we do know that our smallest group is at 81 right now, which is certainly large enough for assessing the discriminant analysis, because if you recall, some of these tests, you don't want to have like a lower cell size than, let's say, 20. So we've got, robust group sizes, and looks like just a couple of univariate outliers, so that should be pretty good. So let's look at the multivariate outliers now. And as you may recall from doing this before, we have to run a regression. And so in order to find those outlier statistics. And so what we're going to do is actually turn the split file off. So I suppose it doesn't really matter which order of those frequencies what we did, whether we did the split file first and then the not split or whatever. It just helps to compare them. So as long as you do them each way, then you are fine. So we will turn off the split file now. Do not create groups. So click on that top one. Click OK. All right. So now we are going to analyze regression linear. And now in this case, let me see. Yeah, so the work status is the dependent variable. I just wanted to make sure I didn't get that wrong. And all those predictors, locus of control, attitude towards current marital status, attitudes towards role, and attitudes towards housework. Those are all going to be our independents. And what we need is the Mahalanobis distance with those outlier charts. Now the book tells us that the critical chi-square value for the outliers is 18.467. So we're just looking for basically any values that would be higher than 18.467. So let's, I think, you know what, collinearity diagnostics would be good as well. So click on that. I don't know what the covariance matrix will tell us on the regression, but you notice a lot of these terms are the same. It's because these tests are all kind of related. They're measuring different aspects of the same thing. We don't need any plots. We don't need to save anything, even though that has the Mahalanobis distance choice on it. That just creates it as a new variable rather than actually showing us the outlier chart. So what we need to do is click paste here. That will bring us to a syntax editor, which I have one already because I'm going to show you something else later. So spoiler alert, don't look at this. But here we're going to erase this period, click enter, and click here residuals equals outliers, and then in parentheses the Mahal one, period. Okay, if you don't have that period, it won't run. Click on regression right here, so you have your cursor in the right place, and then go ahead and hit that triangle button and run it. And here what we have, if we go over to our output, is our regression. And so we really only care about the collinearity diagnostics, which we'll talk about in a second, and our outlier statistics. So remember that the number we're looking for is 18.467. We have two cases that are above that number. So interestingly, if you notice where it says case number 1 and 2, that is not the case number that the book will refer to because they're looking specifically at their case sequence variable. we're going to find that in a second, but here, case 1 and 2 is actually the lines that it's on in the data set. So if we go back to the data set, and we see here's case 1 and 2 right here. So these are the ones that have the multivariate outliers, and they are also the same ones that we had the univariate outliers. The reason that they're cases 1 and 2 is because we sorted by ascending, and so these low scores of 2 here are on the first 2 lines. So these case sequence numbers, 346 and 407, do match what the book says. So we are going to delete those cases as well. Again, they're both in group number 1 on the on the work status, which is the largest group. So we're not really hurting too much by getting rid of those because our group numbers will still be quite high. So we will go ahead and click on both of those and hit delete. And now we have our final number, which if you scroll down is, drum roll, I know somebody's out there doing a drum roll right now. Here it comes, wait for it. All right, 456. And so that's our N right there. So we are done deleting missing cases and outliers. Let's click save because now this is our new data set that we're going to be working with for the rest of the analysis. And now let's talk about linearity. This is where I was trying to avoid splitting the file, unsplitting the file, splitting the file, but I am being inefficient at the moment because of the order that they have these assumptions placed in. So for linearity, we're actually going to split the file again. Where our collinearity diagnostics come in is when we talk about multicollinearity. And so that is where, if you go back to your output and you scroll up, capture this I do screenshots and then crop the photo to just include, this part of the chart that I want, but you're going to put this in the multicollinearity section. And so let's just talk about that right now while we're here. Remember from the previous assignments that the condition index needs to be below 30, which it is. And if it approaches 30, which it's a little bit up there, we have to make sure that in the 4 predictor variables, there is not more than one that's 0.5 or higher. So in this case, we just have the one value that's 0.55. So this assumption of multicollinearity is met. So we can go ahead and save our output just to do that. And then singularity is not an assumption you can test for. It's a logical assumption. We've talked about that in previous examples. And that is essentially saying that each of the variables that we're measuring is measuring something different. If you had 2 variables that were measuring like 2 parts of the same thing, then that would violate singularity. But if each variable is measuring a distinct and separate thing, then you're all set on singularity. So that's just, logic that's going to help you figure out how, what your scales are measuring and whether or not that's singular. So minimize that output now, and we will go back and look at linearity. And so this is really looking at how our predictor variables relate together for each of the different groups. And so that's why we need to go back to splitting our file. So data, split file, go back to organize output by groups. It's already listed there. And make sure sort the file by grouping variables is listed, since we've played around with sorting the file by different ascending variables. We want to make sure that it's sorted. So keep that clicked on and click OK. And then we can go here and do graphs, legacy dialogues, and scatter dot. And we want a matrix scatter, and we're going to define that. Okay, so now we, our matrix variables are the 4 predictor variables. So we'll put those in there. And that's actually all we need to do because we've already split the file and we want to compare the output by the groups. That should just automatically give us the matrices that we want. Let me just look. Yeah, I don't have any other notes on that, so I think that will work. So let's go ahead and just click OK and see what we get. Yep, so that was all we needed to do. And so here we have individual scatter plots for each comparison of each of the variables for each of the groups, if that makes sense. So you're comparing locus of control and attitudes towards housework here, and locus of control and the attitudes towards women. And this is for the working women group. So hopefully that makes sense. It's a comparison of each, and these empty ones here are where the variable is meeting itself, because obviously that's going to be a perfectly linear relationship. So here we're looking for kind of oval shapes, and I know that this looks a little bit funny. I believe that's because locus of control isn't as kind of wide of a range as the other scales, and so it is a little bit different. It's perhaps that's why they labeled it as ordinal instead of scale. I'm not sure. Either way, we're not seeing anything particularly problematic in these scatter plots. And so I think the things that you would be alarmed by would be like U shapes or upside down U shapes, but kind of a nice blob is good, or kind of many data points throughout here. So these charts show us that we meet the assumption of linearity. So you can put that. Let's save this. And now let's see what is next in our list. Okay, the homogeneity of variance covariance matrices, we're actually going to find out when we run our main analysis. We're going to click on the boxes M test. And so we're going to actually do that now because, spoiler alert, we're going to have to run the main analysis twice because the boxes M test is going to be significant and we're going to have to adjust for that. The book describes a quadratic procedure that is going to be necessary because the boxes M test is significant. SPSS does not do that, and so I will show you how to do the same thing in a different way once we run this. So let's remember now to unsplit our data file, because now we are back to wanting to analyze all of the cases. Okay. So now we're going to do a discriminant analysis, but again, this output is not going to be the one we're going to keep because we're going to have to do it a different way. So click on Analyze, and discriminant analysis is under here by Classify, and then Discriminant. Oops. Okay, so our grouping variable is our work status. We have to define the range, and unless it's highlighted, it won't let you click on this button. So let's say I go down here. Now, oh no, how do I define the range? So you have to click on it, define the range. And we have 3 groups, and their labels are 1, 2, and 3. So our minimum is 1, and our maximum is 3. And our independents, we know, are locus of control, attitudes towards current marital status, attitudes towards role of women, and attitudes towards housework. We're entering them together. And let's just look at the statistics here. We want boxes M. We're going to want a lot of these other things later, but right now we're just looking for the homogeneity of variance covariance matrices. So we'll just look at boxes M for now, and then classify. We are going to compute from different group sizes because we have one group that's so much larger than the others. So we will adjust the probabilities. So if you think about probability, if you have 3 groups, what's the random chance that you would correctly pick one of the groups? It'd be 33%, right? A third of the time you'd be correct if you're just picking between groups 1, 2, and 3, and you're randomly just putting cases into each group. You'd be right 33% of the time. If you have one group that's larger than the other, obviously it's not going to be an equal third. So this prior probabilities adjust for that. We're going to leave it at within groups right now. We're going to come back to this though, because that's what we're going to have to do to fix this boxes M problem. So we will just click continue on that, and we won't do anything else for this first run. So we'll click OK. And here we have just the group statistics. That's not important right now. We want to scroll down to this, test results boxes M. Here we have significance. That is not good, because that means there is some heterogeneity of variance covariance matrices. However, as you've probably read in the book, boxes M is a very sensitive test. And so we can actually try to look into it a little bit more and see maybe where is the problem. So we could actually go back and do a one-way ANOVA to actually look univariately at the test of homogeneity of variances. It won't tell us the same exact thing, but it might give us a clue. Essentially, we're looking for the Levene's test. So that's what we're going to do next, to just see, is boxes M being a little bit too sensitive and we can still proceed, or maybe we need to do something about it. So click Save, and then we'll go over to Analyze, Compare Means. We can get to the one-way ANOVA that way. And we are going to use the work status group as the factor, and then our dependents are all of our predictor variables. So you see again how in the beginning of this video I was getting all my terms a little bit confused because in our discriminant analysis, these are the predictors, and here they're called dependents, so it gets a little confusing, but all of these tests are related. So let's look at contrasts. No, that's not what we need. Options, perhaps. Here we go. Homogeneity of variance test. That's going to give us the Levene statistic. And then if Levene's test is significant on any of the variables, then we will know that we do not meet this assumption. So let's click OK. And here we have our test of homogeneity of variances. We're just looking for significance here on each of the variables to determine whether or not the boxes M test is specifically showing up. And as we can see here, we have significance on the variable attitudes towards current marital status. So there's some heterogeneity in the variance covariance matrices. That's, again, the comparison of the within group and the between groups variance. So we do not meet this assumption for this test. The other variables are okay. So that means we have to account for that discrepancy. That's what the book talks about as the quadratic procedure. We cannot do that in SPSS. So the way that we do that is to run our analysis again. So click on Analyze, Classify, and Discriminant. All these things are the same and we still enter them together. But when we click on Classify right here, we are going to use the separate groups covariance matrix. That will adjust for the fact that we did not get homogeneity of variance covariance matrices. So that's how you do that. And then the plots, let's get all of the plots and click on continue. Statistics, let's get everything. We want the means, univariate ANOVAs, Fishers, unstandardized. Some of this we'll use and some of it we won't use, but I'd rather run my analysis getting everything, and then I can understand what I'm going to use and not use. So here we can click continue, and that is it. So now we click OK, and it gives us a warning because it's saying, hey, did you mean to do that? Normally you wouldn't want to do that. If there are fewer functions than variables, that makes a difference. So we do have 2 functions versus 4 variables. It doesn't tell us what difference it makes, but in this case, we can rely on the fact that this is doing what the book needed us to do of separating out the groups. So that's okay. We are going to scroll down now. This is our main analysis. Now here, we are going to come back and look at all of these group means and covariance matrices and everything. Here we're scrolling down to the boxes M again, which here is significant. But if you keep going, there's a different boxes M test that looks at the covariance matrices of the canonical discriminant functions. This is because we did it that way of separating the groups. It creates these canonical discriminant functions, and so really we can now go down and look and see, okay, good, boxes M is not significant anymore. So that's because we separated out the groups. It compared, instead of comparing the within group covariance matrices, it just looked at the differences in between the groups. And here's our prior probabilities for the groups. So it kind of puts it in the order of how weighted it is, what percentage of the sample is each of the groups. So that shows the prior probability. All right, so let's go up to our main starting point right here, the summary of canonical discriminant functions. So think of this as being where your real output starts for the main analysis. Up where we have the means and all that, we're going to look at that later. So just start with summary of canonical discriminant functions. We have the eigenvalue here, or the eigenvalue, I don't know. And that we are actually not going to need to report, but it will be similar to the effect sizes that we get. And so that's just something to note. The first thing we're looking for is the variance accounted for through each of the functions. Now remember, the function is essentially an equation that figures out how to most accurately predict group membership. And so here in the very first function, it accounted for 68.6% of the variance between the groups. Here's our canonical correlation, which is the 0.267. We are going to report that variable when we write it up, and we are going to list degrees of freedom when we do that. There's 8 here and 3 here. Now, this is where you should stop reading the book because it has the SAS outputs, which are calculated differently. We are calculating the Wilks lambda by the chi-square. That's what SPSS does. And the SAS calculates it by, let me look that up real quick. Let me see their output. Sorry. Oh, by the F value, right. So we have chi-squared, they have an F value. So the way that they report that, they're going to have an F and then parentheses 8 degrees of freedom, and I think they have like 900, and then 3 and 451. You're going to see that, and we cannot replicate that because we're measuring it a different way. So what we really care about is this significant at all? Back to our first research question here, does the combination of the predictor variables give us enough information to predict which group they would be in? And so as you can see, the two equations together account for 100% of the variance. So all of the variance is explained by these equations. If they're significant, then both of those equations tell us something. So here in this case, the first function is significant and the second function is significant. So when we type this up, you would report the chi-square value with the degrees of freedom equals the Wilks lambda. I think that's how you would, you do the chi-square parentheses degrees of freedom 8 equals 49.00. When you're reporting in APA, you only need to go to 2 decimal points, so all of these you'd have to kind of round. Okay, so you would report the Wilks lambda with chi-squared parentheses 8 equals 49.00 with p being less than 0.001. And in this case, p is equal to 0.001. So that's how you would write up. So, okay, we know that it is possible to predict which group they would be in a significant way. That doesn't mean you're going to be right 100% of the time. We're going to get to that when we look at our classification results. But basically, we can explain all of the variance by these predictors. And so that is how we can continue on in our reporting. So first, after we report the significance, we are going to calculate the effect size. So the effect size is called canonical R squared, and you can write it as a capital italicized R with a subtext small c and then a squared up in the top. So it takes a little doing, but that's how it would be written. And so what you do is you basically say for the first function, the effect size is 2.67 squared, which ends up being 0.07, again, very similar to our eigenvalue. Then for the second function, the effect size is 0.184 squared, which would mean 0.184 times 0.184, and that equals 0.03, also similar to our eigenvalues. So that means that that is the effect of the combined predictors on these equations and the amount of variance that there is. So in order to find the confidence intervals for this, to calculate this, you need a calculator. So let's save this output, and I will show you a website that I found that is right. Oh, here it is. So it's a free R-square confidence interval calculator. So it's because we're looking at that canonical R-squared, this will work for us. So this website is danielsoper.com/statcalc/calculator.aspx?ID equals 28. So that will bring you to this confidence interval calculator. How many predictors do we have? We have 4. Type that in there. Our observed R squared, remember we have 0.07 and 0.03, so we'll have to do each of those. And our sample size is 456. So we calculate that, and for the first function, our 95% confidence interval is from 0.025, or you could round to 0.03, and to 0.11. So that's our confidence interval, 0.03 to 0.11 for the first function. Let's do the second function, which we'll just change that to 0.03, calculate. And here this gives us the 95% confidence interval. So that's 0.00 to 0.06. Later on, they calculate effect sizes when they do some specific contrasts. And this calculator may not work for that because this is the R squared value. I didn't try it. I kind of just trusted the values in the book. With as far as the confidence intervals goes, I calculated the effect sizes, but I'm just noticing this ad. How does emergency contraception work? Why don't we click off of that now and go on to our output again here? Okay. Sorry for the advertising. So yeah, essentially, you can see if that calculator works when we get to the effect sizes and the contrasts we're going to do, or you can just use the values in the book. So that's up to you how deeply you want to dig into that. I could not find a confidence interval calculator for partial eta squared, which is what we're going to have later. So it depends on how much work you want to do. Okay, so now we want to look at the classification results just to see how much do our equations help us guess correctly. And so here we look at the classification function coefficients. Let's keep going down. This chart is super cool, but I don't understand what it fully means. So that's it shows the canonical function 1 and 2. So it plots it. I think ultimately what it is, now that I stop to think about it, is each individual case plotted. So you know that equation that we were making with the coefficients, if we had the z-scores and we could calculate for each case what the combined score would be, and that combined score would let us predict what group they're in. This is the actual predicted values for each case and predicting what group they're in. And it's plotting it by the first equation answer, by the second equation answer. So that's what that is. But we're not going to need that right now. We're just looking for the, oh, where's my classification little chart? Somewhere in my output originally, I had a little chart that told me how the percentage of accuracy of the classification. So maybe it's up here and I missed it. Or else I didn't click on a certain button that I wanted. Okay, well, I am sorry to say I don't remember how to get the classification results. There must be a chart that I could have clicked on. Let me go back to the, oh, here we are again with that. Let me go back to the data set and just pretend like I'm going to do the discriminant classification again just to see statistics. I had clicked off everything. Classify. Oh, I must have clicked on summary table. So we're going to do this again, and just to get that but the results will all be the same except for the very bottom. So we'll just see, yeah. So going to the very, very bottom of your output, here it's 54.6 of the original group cases are correctly classified. So it shows you, okay, this is how many they predicted were going to be in the working group, was 205. Well, we know the exact total is 239. So some of them, they guessed wrong. Based on those equations, they guessed wrong. And that's because, you know, we don't have as strong of an effect, you know, of the variance explained as maybe we could if the variables, you know, explained more of the differences. So the more accurate the predictors are, then obviously these numbers are going to be pretty close. But still, we have 54.6% correctly classified. And the book mentions that after adjusting for the group sizes, the random chance number, instead of being 33%, would be 39%. And so, but 54% of the time is better than 39% of the time. So that is a sufficient difference. And it's showing that, yep, once again, we knew it was significant, but now we can see kind of the practical implications of how that would be. So that really describes that first section. If you're looking at the checklist, the variance accounted for and the confidence limits for each significant function. So we found the variance explained with the canonical correlations, giving us our effect sizes and confidence intervals. And so we know that basically right now, all we know is that the combination of predictors does in fact help us predict group size. Now, one thing we didn't look at yet is the standardized canonical discriminant function coefficients. So these are the parts of the equation that help us predict the group membership. We need the standardized classification. Keep scrolling up. Here we go. This is right underneath your significant Wilks lambda. Here we have the functions. So these function coefficients would be the numbers that would be in the equation. So it would be for the first equation, the composite score, meaning the combination of all the predictor variables that we're going to help guess the group it's in. You would do 0.135 times the z-score of locus of control plus 0.560 times the z-score of the attitudes towards marital status minus 0.498 times the z-score of the attitudes towards the role of women, and then plus 0.355 times the z-score of the attitudes towards housework. Now, I'm not telling you to actually calculate this. We don't have the z-scores. What we could, I think we would have to use a log function to calculate those. So I'm not telling you to do that. I'm telling you this is what the analysis did for us. And that's what ultimately these plots are going to show us. It's going to show us the composite z-score using these coefficients for the first equation or the first function, and then for the second function. And together these explain all of the variance. So, and also we're going to talk about the structure matrix, but not yet. First, we're going to look at our plots. So now that we understand we're looking at essentially the plot of two composite z-scores that give us a total picture. Think of it as like the combined score that adjusts for the importance of each of the different predictors. We're going to go down here to our plots, and the group centroid, think of that as the the central composite score or the mean composite score. And here in the first equation for the working women, it's pretty close to 0. and here it's pretty close to 0 as well. So that's kind of right in the middle. So then if you look, there's for each of the groups, and then it plots it in a combined plot. And so it shows how these groups relate together. So if we think about the equations for a minute, because it's looking at the variance, I would normally say within the groups, but because of we didn't meet the assumption for that, we are looking at the variance between the groups. But even in that, what we're seeing here is that the composite score for all 4 of the predictors is a bit higher here. See, it's above 0 this way and this way. For the dissatisfied housewives, it's a little bit below 0 here, and this is pretty close to 0. That's kind of probably what they would kind of use as our comparison. And so for the working women, if they're kind of like the close to 0 group, the unsatisfied or dissatisfied housewives have a little bit higher composite score. And the satisfied housewives have a little bit lower composite score. So what that means, if you think about what these scales are, and the book does tell us that these scales, a low score on any of these scales is a more favorable attitude. So if you think about the attitude towards current marital status, a lower score would mean that you have a more favorable attitude towards your current marital status. For the role of women, it's really, I think, based on what the book is saying, looking at the traditional role of women. And so essentially, if you have a low score, then you would have a more favorable attitude towards broader roles of women, whereas a high score on the role of women would mean that you have a more traditional view. You have a less favorable attitude towards women having multiple roles. So it is important. It's difficult in these assignments and using the book because it's not your data set. It's not your data question. You didn't construct the scales. So you have to wrap your head around what these scales are actually telling us. But when we look at this plot, essentially what it's helping us see is that the combined score for all of the predictors for the dissatisfied housewives is a little bit higher, meaning that they have more negative attitudes overall combined. And this score is a little lower, so they have some more favorable views combined. And then the working women is kind of a comparison group. So hopefully that makes sense, but you have to think about this plot as telling you the composite score. Right now, it doesn't tell us anything about what their scores are, and that's why we're going to compare the means later, because this is going to help us understand kind of where the differences lie. So now we're going to look at that structure matrix, also known as a loading matrix. So let's scroll up here. And so structure matrix, where are we? Here we are. Okay, so here's your structure matrix, and it's going to show us which of the variables were kind of like the most influential in the first equation or the first function, and then which ones were the most important in the second function. And so remember that the first function explains more of the variance. And so the attitudes towards current marital status and the attitudes towards housework explain more of the variance in the first equation, and the first equation was more significant, right? More important. Both actually statistically more significant as well as accounting for more of the variance. So that gives us our first clue when we think about the composite score and what's influencing it the most. It's the attitudes towards current marital status and the attitudes towards housework. So that's initially what makes the groups the most different. And then here in the second equation, it's the opposite, and you have the attitudes towards the role of women explaining the equation the best, with locus of control next. Now, of all of these, notice that locus of control is the lowest. That's actually going to correspond with our means that we're going to find, but ultimately what this is saying is that this is looking at correlations. You can see down here it says the pooled within group correlations. And it's looking at the variables and the canonical discriminant functions. So again, this relationship between the predictor variable and the equation, these were the most important, and then these were the most important. So that's what the structure matrix tells you, and you don't have to calculate anything else. It just shows the impact of each of those variables when you're predicting the group membership. So it really is kind of in order here, 1, 2, 3, and 4. In terms of the importance, how important is that predictor in the composite score and the overall comparison? So now we're going to talk about effect size. And we actually, we already talked about effect size. So it's listed again in the in their little list, but I talked about it earlier when we calculated we used the canonical R squared, and we did that with the power calculator or the confidence interval calculator. And so that part we already covered. So if you were going in order of that checklist, you could refer back to that part and calculate. Remember, it was 0.07 and 0.03, which is similar to these eigenvalues. It shows the effect of the combination of predictors on the group membership. And so you can report those canonical R squared with the confidence intervals. So now the last bit before we compare the means, and this was the most complicated part for me to understand and know how to do, because the book talks about these contrasts, and it talks about 12 different comparisons that they used, and they have output for that. Let me find the section. Yeah, it's table 9.11, or maybe in the 6th edition it would be table 11 and table 12. These are 12 different comparisons. Essentially, it's comparing every predictor variable as the dependent with the others as covariates for each of the 3 groups. So you've got 4 predictor variables, 3 groups, so it's 12 different comparisons that you're doing. And what that is going to show us is basically the effect of each of those predictors independently. And so there's 2 ways I figured out how to do this. I did find some syntax online that works with SPSS, and the only reason that the book is helpful on this is to give us a little bit of a clue about the syntax based on how the work stat variable is understood. So what you would do, and I have this set up already in this syntax editor. All right, so that was from our regression, but going up here, and let's click save on this. Okay, so here we're going to do an analysis of variance. We're taking each predictor variable at a time and holding the others as covariates. And we're doing it by the work status group. So what you would want to do, and I'm not going to click OK on this because I don't want it to calculate and wreck my syntax, but because we're going to need the syntax, you would do analyze, and then you're running a general linear model, univariate, because we have covariates. That's why we can't run just an ANOVA. Your dependent variable is going to be, just pick one to start with, one of the predictors. The other three predictors are the covariates. And the fixed factor is going to be the work status. Okay, so now if you click paste, I'm trying to think if there's, no. I tried to play around with contrasts, hours, I can't even tell you. And the only way to do it is this syntax. So you would click paste, and what that would do is bring you to the syntax editor. You would have everything so far correct. I think what I do, locus of control, so I think it's this one. Control by workstat with @mar @role @house. You should have all of this. Oh, if you don't have print eta square, you can go back and check that off. Let me see. Means no. Sorry, I can't remember. Options. Oh yeah, estimates of effect size. You do want that checked off because you want those partial eta squared. Since we're going to be looking for effect size, that's important. Okay, so make sure you have that checked off. Again, that's going to show up in your syntax automatically when you click paste. Or if you missed it, you can just add this little line, print eta square. You'll have the criteria in there. The design will be these four variables, the 3 plus the workstat. Okay, so this is the syntax that matters, and it's the same for each one. So essentially, here are our 12 comparisons. We're doing it in 4 runs. The first one, again, it's just each variable being the dependent. So 1, 2, 3, 4, you have those. They're all by workstat with the other 3 as the covariates. So make sure that what you can do, what I did is like copy and paste this once I get one done, and then just change around the variables to make sure that each one is a dependent in one spot and a covariate on the other spots. Now here's where it gets tricky, and this is what the book did, where the SPSS syntax is this L matrix. It's showing us the combination of the groups. And so this is where the book actually does give us a clue. The -2, 1, 1 is going to be our first comparison, and that's going to show us the working women compared to the combined other 2 groups. And then this workstat 1, -2, 1 again corresponds with the book, and that's going to show us the satisfied housewives compared to the other 2 groups pooled. And finally, this 1, 1, -2 is going to show us the dissatisfied housewives. So in the output, this is going to have contrast 1, contrast 2, contrast 3, and so it's going to give us all this information. So we have, for each of the variables, we have 3 comparisons that are going to be shown in the output, and all together that will give us 12. Now in Tabachnick and Fidell, table 9.14, which is on page 425, in the 6th edition, that might be table 14. This is their summary of the effect sizes with confidence levels for each. Again, I chose to just use the book's values for the confidence intervals. If you find a calculator, then you can do that. Our results are pretty much going to correspond with the book. And so we'll run that, and then I'll tell you the other method that I did that I made up myself and I thought was pretty clever and actually came out with pretty much the same results as well. So that was pretty exciting, but it took me hours. So we are going to use this easy way. If you have all that syntax, sorry, not the regression, ignore that. If you have all the univariate ANOVA syntax with these the same, so if you just want to pause the video on that, I'll kind of show you each one. The matrix is the same on the bottom for each one, but you can see there's 1, there's 2, there's 3, and there is the 4th one. So that's just the 4 predictor variables, each of them being the dependent at the various times. Okay, so we are going to run this, and what we need to do is run it 4 times because it's 4 separate runs. So because the syntax editor doesn't pop right open to the output, we're just going to run them in a row and then look at the output. So get your cursor on that first one and click run. Oh, this time it popped over the output. Okay, well, now we're going to go back to our editor and not lose our place. Do the second one, run. And let's go down to the third one and run. And back to the 4th one and run. Alrighty, now we can look at our outputs. And so you see that this is custom hypothesis test 1, 2, and 3. That's what that L matrix is doing. And so for every single one of these, custom hypothesis test 1 is for the working women group. And custom hypothesis test 2 is for the satisfied housewives. And custom hypothesis 3 is for the dissatisfied housewives. So every time you look at that and you compare it with the table that they have in the book, you're going to see the effect sizes. That's what we're looking for here. And remember that you round up to 2 decimal places, so it's 0.01 right here. So let's look at, let's say, and this also would be 0.01. So this one is looking at the dependent variable of the attitudes towards housework. So let's just look in the book on that table, and the attitudes towards housework for the, in this case, dissatisfied women should be 0.01. Yes, that matches. Let's look at the satisfied housewives group, 0.01 on that attitude towards housework. So that's also lining up with what the book has to say. Then this first one is going to be the working women, 0.00, and yes, we don't round up, so it's 0.00 because that's a 2, not a 5 or more. So those are matching the book exactly, and again, that's where I use their confidence intervals because it's exactly correct. Now that was our comparison for the housework. You see where we got the effect sizes for all 3 groups. Now let's look at, let's see, this one is attitudes towards the role of women. So this here, group 3 is the dissatisfied housewives, 0.00. So now this is a slight difference from the book. They have 0.01. I still use the same confidence intervals. It's still within a pretty close range. Here we have, for the satisfied housewives group, 0.01. Yep, that matches. And then here for the working women on the attitude towards the role of women, partial eta squared here, 0.036, which we do round to 0.04. So that matches the book in their table as well. Again, you can use those same confidence intervals. Now here we are scrolling up to the next variable, locus of control. So that last column in the books table, we are looking for group 3 first, is the, because we're going backwards, I'm scrolling up backwards, that's why it's going 3, 2, 1. 0.01 is we would round, and so that matches the book. Now here it's a little different, 0.002 we do not round up, so that would be 0.00, and the book has 0.01. Again, if you find a way to calculate the confidence intervals, let me know, but I would just use the book otherwise. And then here for hypothesis 1 is the working women. Partial eta squared is 0.00. That matches the book as well. We have one more variable to go, attitude towards marriage. And here we are scrolling backwards again. So we have test number 3, the dissatisfied housewives, 0.01. That matches the book. Here we have 0.02 for the satisfied housewives. That matches the book. And we have, for the first one, oh, went too fast, 0.00, which matches the book. So essentially what we see here is there was just 2 that were kind of stood out. And if you wanted to include outputs on this, because obviously this is a ridiculously long output, I would include the ones that were 0.02 and 0.04. So here, custom hypothesis test 2 on the attitudes towards current marital status. You could take a screenshot of that, and that's one of the variables that for the role satisfied housewives, so the satisfied housewives, attitudes towards marriage has the biggest effect on them being in that group. And then down for when we looked at the attitudes or the role of women, down here, it was, where are we? No, that's locus of control. Let's keep going. Role of women, here we go. We want hypothesis 1 is the working women. That was where we found the 0.04. So again, you could take a screenshot of that, and that would be your output for that one, showing that the largest effect on the attitude towards the role of women, the largest effect in the group membership for the working women is the attitude towards the role of women. So think about this for a second. That means that the working women are most easily classified by their attitude towards the role of women. And we're going to compare the means in a minute, but my guess is that they have a pretty favorable view of women having many roles because they're working women, and so they would have a lower score on that scale than perhaps others. Now, for the satisfied housewives, the attitude towards marriage is the biggest predictor of their group membership. So the ones that are satisfied staying home are the happiest with their marriages, and that's how we can tell them apart from the other groups. So that's what those effect sizes tell us. Now, the other way that I did this, and I'm not going to show you because it's too long and gives you way too many outputs, but I created dummy variables, which is easy to do. We'll close this. You just click on transform, create dummy variables. I'll show you this part. So you want to create a dummy variable for the work status, and you need to call it something. So I would say work stat, and then it's going to say work stat 1, work stat 2, work stat 3 when it creates the dummy variable. So I'm going to go ahead and click OK, and then what you'll see is over here I have work stat 1, work stat 2, work stat 3. So essentially what I did is I turned it into a yes or no question. for the workstat 1, we obviously know it's the working women group. So here, the working women have a 1 in the column, so yes, they are working. And then as we scroll down, we will see it turns right here, there's 239 cases of working women. So then all the rest of them are zeros. So that's kind of an artificial way to combine the other two groups, because until I found that L matrix syntax, I could not figure out how to compare one group with the combined other two groups. And so then what I did is I used those dummy variables to in univariate and COVA. So let me see if I even can remember this. It was late last night. Analyze, general linear model, univariate. And so I would do these one at a time. So I had this as a fixed factor. You pick one of your predictors as the dependent, and then all the others are the covariates. So you kind of have to run this multiple times, switching around. So you would run this one. I think, let's see, options, you would want to do the estimates of effect size, so you get the partial eta squared. And so then what you would do is run this, which I'll show you for a second. Then you'd go back to your data set, run it again, this time switching out the working group for the happy housewives, run it again, and then again for the unsatisfied housewives. So you'd have it 3 times, and then you'd swap out your variables to put a new one in the dependent. And so it's running it 12 times, which is what the book described. And so the dummy variables, kind of automatically combine the other two groups. So that did give me pretty similar results to what the book had. But I did have a little bit of a difference on one where I found significance also on the, let me see. On the role of women for the satisfied housewives. So I had that as 0.02 also. So I made a couple tables that just kind of showed the differences in the ways that I went about analyzing it. But you'll see here, this is the result of what we had found. And this right here is the partial eta squared number that you're looking at. So this was for working women. You can see that it compares the working to not working. This is the 0.001. So for the locus of control, the effect size, I had 0.001, and that was, ends up being 0.00. That's the same as what the book had. So regardless of how you do it, you have to have 12 effect sizes, and you should be able to replicate pretty close to what is in the book, but don't get confused by their syntax because it's not replicatable in SPSS. Okay, so then the last thing that we are going to talk about is the comparison of means, because we've gotten everything in our checklist. We just finished up the variables separating each group with effect sizes. So that shows, we just did that contrast to 12. So now the additional analysis, group means and standard deviations for high loading variables. So we can go back to our original output. Did I close my syntax editor? I guess I did. I guess I saved it and closed it. Okay, so here we need to go all the way kind of back up we need to make sure that we find the discriminant that has this warning on it, so that we are looking at not the very first one that we did, because recall we had to change and look at separate groups because we did not meet the assumption for homogeneity. So here is something that can help us understand the differences between the means for the different groups. So here are the mean scores for each of the scales for the working women, the satisfied housewives, and the dissatisfied housewives. And so that we're going to come back to that in a second, but look at the tests of equality of group means. Notice that everything but locus of control is significant. So basically, if we see the locus of control means right here, 6.72, 6.63, 7.05, those means are pretty close together and they are not significant. So I made a table of just the other three variables that are significant, but you could make a table that had a comparison of all of these variables and the means, and it's kind of, on the left-hand side, you could have working, satisfied housewives, unsatisfied housewives, and then going across on the top, you could have either the three significant variables or all four variables and indicate which ones are significant. Either way, that's a helpful chart and a lot more helpful than this to look at. And so you don't need to, this weighted stuff doesn't matter for our purposes. You can indicate the standard deviations if you, kind of underneath your mean in your chart. It might be helpful. But to compare the attitudes towards the current marital status, recall that was the most, had the most effect on being placed in the satisfied housewives group. So let's compare those means. This is 23 for the working women, 20, and 25. So a low score means you have the most positive attitude. So here we see where that came to be, that the 20.60 is they are the most satisfied with their current marital status. And the working women are kind of in between. And then the dissatisfied housewives are the least happy about their current marital status. So that kind of shows you what the exact differences are in the mean scores. Let's look at the role of women, which, if you recall, was had the most effect on being placed in the working women's group. Here we have a score of 33.86 for the working women, 37.19 for the satisfied housewives, and then let's see, 35 in between. So here, 37 is the highest score and 33 is the lowest score. So that shows you where that contrast is, and is possibly why, in my different dummy variable way of finding things, that I found that was important as well. So they had the highest score, meaning that the least favorable view, a more traditional view of women, that they should stay home, let's say. And this, had a more positive view of women having multiple roles. So those things had some effect on the group membership. And then looking at their attitudes towards housework, 23.81, 22.51, and 24.92. There is significance there, but there wasn't a strong effect on that variable, so we can see the contrast of those aren't maybe so great. They're significant, but they don't have a strong effect. So that is how the group means help us understand what we found when we were looking at the combined variables. So all of these tests, ANOVA or MANOVA, any of those, they tell us, is there a difference? Yes. And then we have to do all these other kind of analyses to look at how are they different. what difference does it make? Because that's when we can actually draw conclusions. And so that concludes all of the tests that I ran for this example. You can type that all up along the lines of what they did in their summary report, which is for the 5th edition on page 426. It's the little boxed out section that says results. And you can follow along what they did to show how to report some of these things, but keep in mind, it won't be exact because they did calculate some other things that we didn't. And so they have some extra stuff in there. And, but otherwise it's pretty similar. So you can ignore kind of like the jackknife part and the pooled within group correlations part that they have towards the end of their description. I hope that's been helpful, and I hope you understand discriminant analysis a little better, and thanks for watching.